So good morning to one and all. This is Amanat Sharma, faculty from ECE department, CPR it's called. So I am dealing with the course Signals and Systems, and in that course discrete time Fourier transform is the third unit. So here I would like to give information about this particular. It is very small unit in the entire course, having only definition and properties. Only two are major concepts, and problems is usually needed. So basically it is having only two: definition of DTFT and the property of DTFT. And the DTFT derivative problems have been discussed in the material very elaborately, but here in PPT it is not possible to discuss those problems elaborately, but I will give the idea how to solve the problems in the DTFT, and it is very simple, and you people definitely has to go this unit because it's a definitely you get a good marks, because according to the rules of JNTU, every unit must to carry one particular question, but in this unit entire the questions only carries maximum of three varieties: definition, property and problems. No other things will be there. So it is very easiest unit. So people should read this unit, and moreover this unit is very basic unit for next further courses like digital signal processing in that, and digital image processing in that. You will use these basics to understand those courses. Okay, thank you. And the DTFT, the discrete time Fourier transform, the name is clearly showing what is this particular. So Fourier transform, it is a general Fourier transform, but you have to apply the Fourier transform to the discrete time sequences. So we have to apply sequences. Sequence means discrete, and previous unit continuous time Fourier transform, it is discrete time Fourier. So both are having same methodologies, but the difference is there we are using integration, here summation we have to use, sigma we have to use. So let us take the definition of the DTFT. So discrete Fourier transform. With the definition, discrete Fourier transform should be applicable to the discrete sequences x of n. For continuous Fourier transform is on non-periodic, periodic time sequences x of t. Okay, it is so discrete. It is also complex one, so it is having magnitude as well as phase spectrums. And the DTFT of a sequence is defined as x of e power j omega t is equal to sigma n equal to minus infinity to plus infinity x of n e power minus j n omega naught or n omega. Sometimes it can be x of k also they will write. So you don't worry about, no need to worry about that things. Okay. So here they will represent kn equal to e power minus j omega, they will write. In some textbooks they follow the notation like this, but we are following this notation. Okay. So inverse DTFT is x of n is equal to 1 by 2 pi integral over 2 pi x of e power whatever you are finding, e power j omega into e power plus j omega n d omega. So that is inverse DTFT. DTFT pair is represented as x of e power j omega into Fourier transform of x of n. X of n is inverse Fourier. So x of n is f DTFT, x of e power j omega. E power j omega sometimes they call as k, small k in some textbooks. Okay. Next to the DTFT Fourier transform is always, remember, it is always periodic function with periodicity 2 pi. That is x of e power omega j into omega plus 2 pi is equal to x of e power j omega. That is, you can say this as a first property also. Some textbooks they write this as a property, but there is a general thing, general nature of the discrete Fourier. It is always periodic in nature. Okay. Next, coming to the properties of periodic DTFT, first one is linearity property. As we know, alpha and beta are constants. Alpha of x of n plus beta of x of n is Fourier transform paired with alpha of x of f, that is Fourier transform by f. So alpha of x of n, alpha of n, z of n is equal to alpha x of n plus beta into y of n, alpha and beta. Then substituting z of that is we are calculating Fourier transform function DTFT of theta of 10 is equal to sigma n equal to minus presence substitute this function here e power j omega plus pi and substitute 2 pi f, no need to worry about the permutations, and this is equal to alpha x of f plus beta pi of f. So the derivative property has been justified. Next, time shifting property. The time shifting property is if x of n is Fourier transform paired with x of omega, then Fourier transform of DTFT of x of n minus m is having its DTFT paired with e power minus j omega m into x, where m is a positive integer, and again where m is an integer. So f of x of n, so directly taking in this function, sigma n is equal to minus infinity to plus infinity, the function x of n minus m into e power minus j omega. Put n minus m equal to p, implies n is equal to p plus m. Therefore, f of for a discrete DTFT of x of n minus m is equal to limits also changed from p. So x of p into e power j omega. Again, the rewriting this into e power minus j omega p into e power minus j omega m. So this function is this one. So Fourier transform of x of n minus m is equal to e power minus j omega m x of n. Time shifting property has been proved. Next, frequency shifting property. If x of n is Fourier DTFT with x of omega, then DTFT of x of n e power j n omega naught is equal to x of omega minus omega naught. So again, taking the Fourier transform of x of n e power j n omega naught is equal to sigma n equal to minus infinity plus x of n into e power j n omega naught into e power minus j n omega. Again rearranging the function, because here bases are same, you can add the powers. So it is equal to x summation n equal to minus infinity plus infinity x of n e power minus of j into omega minus omega naught into n. Now compare the standard formula with this notation. So x of n, there x of n, instead of e power j omega we are having omega, instead of omega n we are having omega minus omega. So it is DTFT of x of omega minus omega. Compare it with the standard formula. So it is x of omega minus omega. Hence the property is true. Next, time reversal property. Time reversal property means if x of n is DTFT paired with x of omega, then x of minus n is DTFT paired with x of minus omega. So taking the for DTFT of x of minus n, sigma n equal to minus infinity to plus infinity x of minus n e power minus j omega n. So reversing x of minus n of minus n, this you can write this as double reversing. You have to, by double reversing it is x of n into e power minus j omega. You can write x of n into e power minus of minus j omega. So instead of omega we are having minus omega. So x of minus omega. First reversal minus n will be removed. Second reversal positive n will be removed. So you will get the standard form. We are converting the summation into standard notation, which in the standard formula instead of omega we are having minus omega. So it is x of minus omega. This is time reversal property. Next, differentiation in the frequency domain. If x of n is for DTFT paired with x of omega, then n into x of n is DTFT paired with j into d by d omega of x of omega. Let us see this proof. Let's suppose, as we know, the formula for DTFT of x of n is x of omega is equal to sigma n equal to minus infinity to plus infinity x of n e power minus j omega. Now differentiating on both sides with respect to omega, d by d omega of x of omega is equal to d by d omega of sigma c. So changing the order of summation differentiation, sigma n equal to minus n plus infinity x of n into d by d of e power minus j n omega, e power minus d by d omega of e power minus j omega not equal to minus j n into e power minus j omega. So substituting, letting this j omega into left hand side, we will get rearranging this summation, we will get the statement like this. So this is how we can take the differentiation property in frequency domain. Next, convolution property. So convolution property states that as early stage you have a convolution time domain results multiplication in its frequency domain. Similarly, convolution in nth domain results multiplication in its harmonic or frequency domain. So x1 of n, x2 of n. I am taking two functions, x1 of n and x2 of n. x1 of n is DTFT pair with x1 of omega. x2 of n is DTFT pair with x2 of omega. Then Fourier transform of x1 of n convoluting with x2 of n is equal to x1 of omega into x2 of omega. So to get the proof, first we have to define the convolution sum in the discrete functions. So the convolution sum in the discrete function will be defined like this: x1 of n convoluting with x2 of n is equal to sigma k equal to minus infinity to plus infinity x1 of k into x2 of n minus k. So f of x1 of, then taking the Fourier transform for this function, DTFT of f of x1 of n convoluting with x2 of n is equal to sigma n equal to minus infinity to plus infinity x1 of n convoluting with x2 of n. This is the function into e power minus j omega. Substituting this convolution sum formula in this equation, double sigma, we are having double summations. Next, interchanging the order of summation, f1 x1 of then sigma k is equal to minus infinity plus infinity. I am letting k this outside, x1 of k into sigma n equal to minus infinity plus infinity x2 of n minus k into e power minus j n omega. So applying the time shifting property, or n minus k equal to some constant p, if you take, so n minus k, so n is equal to p plus k. Substituting that function j omega into p plus k. So again, this is the formula for x2 of p into e power minus j omega p is the formula for the DTFT of x2 of p, that is x2 of n, x2 of omega, and it left with e power minus j omega k. So x1 of k into e power minus j omega k with k, it is the formula for DTFT. So like this, you can rearrange this summation into this form. It left with x1 of omega into x2 of omega. So multiplication, convolution in nth domain results multiplication in its frequency domain, convolution formula. Next, frequency convolution property or multiplication property. In other words, you can say that multiplication property. So multiplying time domain results convolution in its frequency domain, or convolution in frequency domain results multiplication in its time domain. So again, I am taking the here. I am interested to solve by taking the inverse for a DTFT function. So Fourier transform of x1 of t and x2 of t is equal to x1 convolution with f2. So x1 of t convoluting with x2 of t is 1 by 2 pi integral minus pi to plus pi x1 of theta into x2 of omega minus theta d theta. Proof. For f of x1 of n into x2 of n is equal to sigma n equal to minus infinity to plus infinity x1 of n into x2 of n into e power minus j in omega naught. Now substitute the inverse Fourier transform of x1 of t. So inverse Fourier transform formula of x2 of t, 1 by 2 by integral minus pi to plus x1 of theta into e power j theta n into d theta e power minus j omega x2 of n. So now interchanging the order of definite, letting 1 by 2 pi outside of the integration, information x1 of t, x1 of omega into sigma n equal to minus infinity to plus infinity x2 of n into e power minus j into omega minus theta into n d theta. So again, applying the time shifting property, it is applying omega minus theta. So it is the frequency shifting property, applying the shifting property. So it is x2 of omega minus theta, so which is nothing but the formula for the convolution sum, which is given here. So it is convolution sum of x1 of theta into x1 of omega into x2 of omega. So next one, an important thing is modulation property. If x of n is Fourier transform paired with x of omega, modulation property means x of n into cos omega naught is equal to 1 by 2 pi x of omega plus omega naught plus x of omega minus omega. So proof, if you take the proof, if you see the proof, f of x of n into cos n omega naught is cos n omega naught e power j omega naught plus e power minus j omega by 2. So again, rearranging this 1 by 2 constant sigma n equal to minus n plus 2 x of n e power minus j into omega minus omega naught plus. So applying the shifting property, it is x of omega minus omega naught plus x of omega plus omega. Hence it is proved. So with this, the sum of the basic property has been given. In the next class, we will discuss more properties and then conclude the unit. Thank you.